Now, like we said in hydrogen, n is the only quantum number necessary to calculate the energy of an orbital. But in multi-electron atoms, both n and L influence the energy of an orbital. Okay? And L goes from S to P to D to F, okay, for the different orbital types, just like we said, from lowest in energy to highest in energy. Okay? And then this little chart right here shows us from lowest energy to highest energy what all of the subshells have for their energies. Okay? So just like we guessed for beryllium, 2 electrons would go in 1s, and then 2 electrons would go in 2s, because that's the next highest in energy. Okay? Boron with 5 electrons would be 1s2, 2s2. Then what's the next highest in energy, sort of based on our little chart here? 2p. Yeah, it'd be 2p1. Okay? We can draw those here in this orbital diagram as well, right? 1s2, 2s2, 2p1. This is a diagram like this is the exact same sort of idea as those boxes and the arrows. Just now we've arranged them going upwards as they go higher in energy. Okay? So sometimes it's shown like this. In a couple of the mastering chemistries that you'll be doing in this chapter, you'll be constructing these sort of diagrams just by identifying the orbital type. Right? You'll click 1s, and it'll put that there. And then you'll click to put its electrons in. And then you'll select a 2s from the list, and it'll put that there, and you'll click the 2 electrons. Now, look at 2p. 2p looks different from the s's, okay, from before, because there are now 3 orbitals, okay, within every p. What shape is a p orbital? Yeah, s was spherical. P had 2 lobes. Okay? So that means for it to be a symmetrical subshell, there have to be 3 of them, right? There has to be an X and a Y and a Z. Okay? That's why there are 3 spaces here in 2p. Okay? All of this entire grouping here is the 2p subshell. Okay? But it contains 3 orbitals. Right? There, there, and there. It has X, Y, and Z. Right? Px, Py, and Pz. Individual orbitals within a subshell, right? That's the next quantum number. That's the magnetic quantum number that shows orientation. But orientation doesn't change energy. So that's why the 3 orbitals within that subshell are on the same level. They're equal in energy, right? Okay. So the orbital diagram of boron, okay, it could be drawn above like that. It could just be drawn in a row just to save space. Let's draw a box for 1s. Let's draw a box for 2s. But then let's draw 3 connected boxes for 2p.
And 2 electrons go with each of those 2, right?
Yep. We fill sort of from the bottom up, low energy to high energy. So we're going to fill those. We're going to do 2 electrons in there, 2 electrons in there, and then just 1 electron in the first of the 2p orbitals. Okay. So you could imagine then the next elements after boron will continue filling this 2p subshell, okay, until it's full. How many electrons will fit into 2p then total? Yeah, 6 will fit into 2p, okay? But that's literally because, here, if we just write the quantum number for this electron right there, N, L, M, L, MS, okay? N equals 2. Because it's a p, what does L equal? L starts at 0, 0 for S. Yep. Because here is L equals 0. Here is L equals 1. Okay. And what does ML tell us? We got size, we got shape. Yeah, size here, shape, orientation. So that goes from -1. So we've got -1, 0, and +1. So that would be a negative 1, and it would be plus 1/2 for an upspin electron. But the reason that we can fit 6 electrons into 2p is because we can start with negative 1, okay, have up or down. For 0, we could have up or down. For 1, we could have up or down. Okay? That's 6 electrons that go within that entire subshell. Okay? One more thing that we're going to see here in just a few minutes, though. Here's 2p. Okay? Next highest in energy is 3s. Okay? Right? As we would totally expect, then 3p. But then what's next highest in energy? So go totally upwards. Right? Hold your pencil like that if you need to. Here's 3s. Here's 3p. 4s is next. Okay? There's overlap involved there. It's because as n increases, energies get closer. Okay? So look, here's 1 to 2, then 2 to 3, 3 to 4, 4 to 5. See how they're getting closer together? But also, as n increases, we have more letters. Right? We have more L's. Right? Because we can go from 0 to n minus 1. So the combination of those n's getting closer together, but also them being divided into more subshells, means they start to overlap. So we've got some overlap there. 4s is going to be lower in energy than 3d. That's going to have a direct impact on the shape of the periodic table as we know it, okay, which we'll see in just a second. So
So is 5s before 4d?
let's take a look right here. Yep, 5s is before 4d. But you don't have to memorize that, because the periodic table will show us exactly what to do. So, alrighty, let's draw electron configurations and orbital diagrams, hydrogen through neon. We've already done hydrogen, 1s1 and 1s2, and helium. Okay. If we're doing our orbital diagrams, here's 1s, here's 2s, here's 2p. Just to give you an idea, 1s1, 1s2. Okay. Why don't you see if you can write and draw the electron configurations and orbital diagrams all the way 1 through, and you don't even need a periodic table. We're just going straight in order here. Good practice. When you get to carbon, read Hund's rule down below the table. Hund's rule will tell you where that second electron in 2s goes. Or in 2p. Let's see if you can figure that out. There you go. That's not quite right because of Hund's rule. There we go. Good. Good. 1s2, 2s1, 1s2, 2s2, 1s2, 2s2, 2p1, 1s2, 2s2, 2p2. Okay, so read Hund's rule. Electrons fill orbitals with equal energy singly first. Orbitals with equal energy mean orbitals within a subshell. Right? Right? We see directly here, okay, changing N increases energy, changing L increases energy, but changing ML does not increase energy. Okay? So different orientation orbitals that are part of the same subshell have the same energy. So 2px, 2py, and 2pz have the same energy. That's what Hund's rule is talking about. Okay? So electrons fill orbitals with equal energy singly first with parallel spins, which means when I'm doing 1s2, 2s2, 2p2, okay, here's our 1s2, 2s2, 2p1. Where's that second electron going to go? Next box over. Okay, there's 2p2. Okay, 2p3, 2p4, 2p5, 1s2, 2s2, 2p6. 1, 2, 3. 1s2, 2s2, 2p. See, now if we're doing 4, we've got 1 in each first. Then we'll start pairing up spins. So there's 2p4. 1, 2, 3, 4. There's 2p5. 1, 2, 3, 4, 5, 6. The reason for that is because electrons repel each other. Okay? So as long as energy is equal, shoving 2 electrons in the same orbital will be repulsive, okay, of each other. So they would far rather be singly in different orientation orbitals, okay, before they start to pair each other up. So the orbitals themselves are equivalent in energy, but that arrangement of electrons could have different energies. Okay? 2 orbitals or 2 electrons within the same orbital are higher in energy than 2 electrons in equal energy but different orientation orbitals, okay, because of that repulsion. So 1s2, 2s2. Okay. So the other thing, or I guess the first way that we'll start classifying these electrons now, we can identify inner electrons now. Inner electrons are a full noble gas electron configuration that's inside of an atom's electrons. Okay? We can abbreviate electron configurations then as long as we have a full noble gas worth of electrons. Okay? So what are the noble gases on our list here that we've talked about so far? Neon is a noble gas. What's the other one? Helium is a noble gas. Okay? So over here to the right, let's make abbreviated electron configurations. Okay? There's no abbreviating hydrogen, right? That's just 1s1. But helium, now that that's a full noble gas worth, we can just write in square brackets helium. Okay? And that means for those that have 1s2 in them, we can just say helium and then continue after that, 2s1. Right? Including things like carbon, right? Helium, 2s2, 2p2. All the way down to neon, which we could say helium, 2s2, 2p6, but that's just neon then. Okay? So then elements after neon, if you're told to write an abbreviated configuration, You just put neon in square brackets and then continue after that. Okay? So the inner electrons for any of these, there are really no inner electrons for hydrogen and helium, but now for at least lithium through fluorine, okay, we call these inner electrons, right? That is a full noble gas. I guess we could include helium in that too. Sort of go either way on that, but okay. Now, this whole thing, once we get to neon, that's inner. Because now neon is a full noble gas worth. Okay? Doesn't make too much difference with these smaller atoms, but as you get down to the bottom of the periodic table, rather than having to start at 1s2 for the very first thing and then going through the whole thing until you get to your element, all you have to do is look backwards until you get to a noble gas and then start with that and continue after that point. Okay? So that's how we make abbreviated electron configurations. Here are the first 3 rows of the periodic table. Okay. You notice I don't have the middle section because the middle section doesn't start until the 4th row. Okay. But 1 through 18 only make use of s and p orbitals. Okay. And what are shown directly in this diagram here, right? 1s1, 1s2. These are now the valence electrons. Okay? The valence electrons are the number of electrons in the outermost principal energy level. Okay? So the largest n, given an entire electron configuration, you would identify all of those orbitals that are part of the largest n, okay? Which could include from multiple orbitals. Okay? So 2s and 2p, for instance, or 3s and 3p, or just 3s if we're over here. Okay? Valence electrons, and then we'll talk about how to do d electrons, okay, in a little bit. Okay? But for elements 1 through 18, we could write their abbreviated electron configuration with a noble gas and then what we've got in these boxes here. So you notice the relationship of those electron configurations with the general shape of the periodic table, right? As we're passing through the first 2 columns on the periodic table, right, group 1a and group 2a, we're adding electrons into an s subshell, right? And then every time that you switch to a different area on the periodic table, right, sort of a different shaped area on the periodic table, you're starting to add electrons into a different lettered subshell. Okay? So that's why we had 2s1, 2s2 over here for lithium and beryllium, but then boron through neon, those are filling in 2p1 through 2p6. Okay? New row, 3 s's. Okay? Then new section. Over here, we're filling in the 3 p's. Okay? So the number of valence electrons just equals the group number, okay, for elements in these areas, right? Number of valence electrons equals group number for what we're going to call S block and P block elements. Because for any element that's in the first 2 or the last 6 columns on the periodic table, okay, S and P electrons will be the only electrons filling in the largest n, as it turns out. Okay? We're going to see how that overlap of those energy levels plays into that here in a second. But it actually makes it really simple that as long as we're filling in S's over here and P's over there, then that's not just for these ones. That's all the way down through the bottom of the periodic table. The valence electrons involve just S and P electrons. Okay? So counting electrons in any combination of an S and P subshell, that gives us that 8 number that we're gonna be looking at quite a bit. But 8 electrons, all that really refers to is a full set of S and P orbitals within the highest shell that there is. Okay? So that's why something like neon has 8 valence electrons. Argon has 8 valence electrons, and it continues on downwards that way. Helium only has 2 valence electrons, but that's a little bit of an anomaly. All the other noble gases will continue to have 8 valence electrons through the rest of the... Let's write that. Eight valence electrons. So it turns out having 8 valence electrons makes an atom particularly stable because that represents a full S subshell as well as 3 full P orbitals. Okay? So it's a combination of that full S and 3 full P's that gives us a completely symmetrical arrangement of electrons within that valence shell. Okay? Now, of course, that's not dealing with D's and F's and other areas. We'll deal with those as we go along. But for the S block and the P block, that's very nicely behaved. Okay. So this is a simplified version of a periodic table showing only the shapes of these 4 regions. Okay? We referred to the S block already, and we referred to the P block already. Okay? And what we can do on a copy of a periodic table down here. Now, hydrogen and helium are a little unique. Hydrogen is just 1s1. Helium is 1s2. Right? But then lithium and beryllium, we're filling in 2s. You can just write it right in between there. Okay. Boron through neon, we're filling in 2p. All right. So before, we're filling in 3s here. We're filling in 3p over here. Okay. It's sometimes helpful to draw a line straight downwards. Showing you the border of the P block over here. Right, here's the S block. Here's the P block. Not counting helium. Okay, but the rest of those all the way down there. Okay, so let's continue writing in subshell names for all of the rest of the blocks on this periodic table. That will allow us to do any electron configuration, and all we have to do is kind of follow along. Okay, so given that this is the S block over here, follow the pattern. What would potassium and calcium be filling into? We'd be filling into 4s. Okay, and that makes total sense with the S block because we're in the 4th row. Okay, and that's the S block. Okay, but that would not make total sense to us if we were just looking at quantum numbers. Okay, because n equals 3 could have 3s and 3p, but also 3d. Okay, because L equals 0, 1, and 2. So where do you suppose 3d is actually going to fit on the periodic table here? Starting with scandium here and going through the middle of the transition elements. Okay, so here's the D block. Okay, so going all through here, this is 3D, up through zinc. But then following 3D is not 3p, it's going to be what over here? It's going to be 4p. Okay? So rubidium and strontium would be what? That'd be 5s. Then Y, what's that? Ytterbium, something like that. Ytterbium through cadmium. What are those?
4D.
That's 4D. Okay. Just draw a line there to show we're filling the 4D. And then over here, indium through xenon would be 5P. Okay, so let's take a little break and look at the pattern here. Okay, for S's and P's, that N number, right, the number that starts each of those subshell names, is just the same as the period number, same as the row number. Okay, 3S and 3P are both in the third row, for instance. Okay, so what we can say in our little diagram up here is that just N equals the period number. We can say that for P as well. N equals the period number. Okay. But for the D block, we cannot say that. Based on what we have written for our Ds here, what is that N equal to? Yeah, period number -1. 3D is in the fourth period. Okay. And the whole reason for that, let me just bring this back up right here. Okay? The whole reason for that is because of that overlap. Okay? Right here is when we start the fourth row on the periodic table. Okay? But the highest energy subshell out of the third shell is actually up here, higher in energy than those 4s. Okay? So those 4s, 3d, 4p, which we just filled in on our periodic table. Okay. 5s, then 4d, then 5p again. Okay. So don't memorize, sort of what order they are in energy. As long as you know these general rules, and the periodic table will guide you as long as you're following along and filling in electrons in the right spots. Okay. So 4d, 5p, got over here. Okay. So what's next then? We got cesium and barium down here, so that's clearly 6s. Okay. Now, after barium, we're going to a new section. Right? This periodic table right here, we've got a little 1 star that links us down here. Okay? So this is the first occurrence of this area down here on the periodic table. So what letter do you suppose we'll start using for that? This is the F block down here. Okay. So the first D was in 3. Okay. I mean, just the way these quantum numbers work, right? N equals 1 was just S. Okay. N equals 2 was our first P, right? N equals 3 had our first D. So what do you suppose our first F will be? Yeah, it's going to be 4F down in here. I'm just going to write it over here. Also, I'll write it in there. I'm making that a different color, right? So you specifically make note of that. That's a very common mistake that students make, skipping over the 4F subshell altogether and just continuing along with the Ds. Okay, but there's the first occurrence of F there. It's in the 6th row. It's 4F. So up here in our F block, we can say that N equals the period number -2. So the periodic table is shaped in kind of an interesting, unusual pattern, but that pattern comes entirely from electron behavior. Okay? We sort of defined the parameters of those quantum numbers, and that came from observation, but it just has to do with the way those electrons behave. Okay? So that's 4F. So then if we did 6S, then went all the way through 4F, then what would come next after 4F? 5D. Then over here, 6P. Yep. Then down here, 7S. Then what? 5F. Put that here. Okay. So 7s, 5f, 6d, 7p. Okay. So take some of my lines out for clarity there, but you get the idea. That is all of the subshells, and that's the filling order of subshells within for any element. Okay? So if we're doing the electron configuration for, I don't know, plutonium, what you would do is literally trace along the periodic table, filling up the subshells of all these electrons as you pass them. Okay? Now, what we need to do, we can use the width of each of these blocks to tell us how many electrons they can hold, right? So we had just a single orbital right over here that could hold 2 electrons, right? An upspin and a downspin. Okay? We had 3 orbitals over here that can hold 6 electrons. Okay? How many electrons can fit into the D block? Yeah, it's 5 orbitals that can hold 10 electrons. Okay? So here, make a little table off to the side here. SP DF max 2, 6, 10. And even without counting, if you can know that this came from 1 orbital, 3 orbitals, 5 orbitals, F probably has how many orbitals? If we went 1, then 3, then 5, then 7 orbitals, okay? That had to do with going minus L to positive L, okay? So it's just 0, then 3, then 5, then 7, okay? So 14 go in F. Yep. But again, that only comes from the pattern of those quantum numbers that we've already talked about. How the magnetic number goes from minus L to plus L. Okay? Negative 3 to plus 3 gives us 7 total. Okay? So, armed with really only that information, we can write a complete electron configuration for any element.